Hello again, everyone. We're going to continue our journey through expressions.v. This time we're going to talk about encodings. Encodings are one of the classic computer science ideas, borrowed, I think, from math, but really has a natural home in computer science, where the idea is that we want to have really simple definitions and we'll build more complicated things on top of that. You might think of a lot of the stuff we've done in Coq already as an encoding, but here I mean something even more particular. Let's think about our BXs. Let's get that open. Inductive BX, that's the first one. Here's the one that we actually want. All right, give ourselves some room. Beautiful. So you'll notice this is a pretty impoverished notion of Boolean expression, right? We don't have or, we don't have greater than, we don't have less than, we don't have greater than or equal to, we don't have not equal to, we don't have any of those. So like that's a little surprising, maybe, that we didn't include those. And in many languages, you just include them. But there's also an approach where you say, well, look, we can express all those ideas with the things we already have in BX. So let's just go with it. Let's see where we can get. So for example, here on the screen, I have this definition BOR, or BOR, maybe too close to home right now. I have this expression BOR that sort of encodes what an OR might be. So what do I mean by encodes? Well, we want B or B1 to B1 B2 to behave like or B, right? The function that we wrote that said this or that, this inclusive or. But in our language of BX, we can only use the constructors that showed up here. There is no or. So we could add a new constructor, or we could say, well, wait a minute. If you give me the expressions B1 and B2, I can construct a term that, okay, it's not literally B or, because that constructor doesn't exist, but it behaves like it. Right? No one will ever be able to tell unless they actually go into the AST and look at it. So here's our encoding of it using one of De Morgan's laws. So the general idea here is noting that B1 or B2 is the same as not, I'll use this notation, not B1 and not B2. Right? It is the case that B1 or B2 is true if it is not the case that both B1 and B2 are false. I have one more paren. I have an extra paren. Right? This is the encoding that we're doing. So like maybe you don't believe me. You could work it out. Build a truth table to prove it to yourself. I think it's a great way to spend your time right now. Maybe pause the video and do that if you like. But another way to do it is like, well, look, build a truth table. Let's just test it. Let's run b-eval with it. So when you've defined your b-eval, this is actually kind of a nice set of tests for your b-eval. Right now, they're not going to do anything because I've got an empty definition right here. But it should be the case that these three will all return true, and this one will return false. All right. This idea of encodings is really powerful. Why is it so powerful? Well, having a small language here means it's easier for you to write an interpreter like b-eval, easier to write optimizations if you wanted to work on that, easier to do analyses to look at your code, right? There's just fewer cases. There's less to think about. And then so long as you can encode all the other operations you want, you're really not missing much. You've kind of got the best of both worlds. You can pretend like you have these big fancy things, or, less than greater than, as we'll have you be doing in a second. But then really in the core language, you have much less implemented and everything else is encoded. This is a really just sort of crux idea in computer science. When you get to CS 101, theory of computation, we'll spend a long time doing encodings between different sort of theoretical objects to sort of say, well, this is just as expressive as that, or things like that, by using these encodings to talk about them. It's a really common computer science technique. Okay, one tiny note here is like we didn't write it this way because there's not really such a constructor. And if we wrote it that way, then it would blend in better, but then people would get confused if they ever tried to use it in a match, because you can't use it in a match. BOR is a function, not a constructor. Okay, so we have an exercise for you here where we want you to implement BLT, not bacon, lettuce, and tomato, as exciting as that may sound at this moment, but less than, greater than, and greater than or equal to, and not equal to. So each of these can be defined with a bit of cleverness using only a single comparison. So what I mean is like, well, one way to do the b less than here is to say that, well, it's less than or equal to, and it's not equal to. But that'll mean using A1 and A2 twice. You'll be doing more than one comparison. So it turns out for each of these, you should be able to implement it using only one of these two comparisons. Okay, at that rate, if you've implemented BLT using only one comparison, you're free to use BLT and BGT. If you're not sure about a definition sort of meeting our requirement, just ask on Zulip. There'll be points for just getting it right, but there'll also be points for writing it in this minimal way where you're doing the minimum number of comparisons. So we'd like you to do these encodings sort of inspired by the encoding you see up here. Okay, the last little bit, the next two videos we'll have are both about compilation. How can we take this arithmetic language down to something that looks more like the processor of your computer? So we'll be talking about that coming up. Talk to you soon.